Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll discuss a new topic regarding the power transmission through pipes. So actually the power is transmitted through pipes means that depends upon the few conditions. One is actually the weight of the fluid which is flowing through the pipe. So the first point is we need to consider what is the weight of the fluid. What is the weight of fluid which is flowing through the pipe? This is first one. And the second part is what is the head? What is the total head which is available at the end of the pipe? So another one is the total head end of the pipe. These are the two things are there. End of pipe. So to identify these things like the power transmission through pipes, we need to follow these two conditions. And to calculate the power transmission through pipes, we need to consider experimental observation. So here we have taken a tank which contains of water and or any kind of fluid maybe you can consider, and this tank, along to the tank there is a pipe is connected to this. So a pipe of uniform diameter, which is a diameter of D, you can see here. This is the uniform diameter of the pipe, and the liquid which is the fluid which is present. This is the upper level of the surface of this water. This one you can say this is the tank, and this is the liquid surface. This is the liquid surface of this, and the pipe which is connected to the tank. At the end of this point, it was mentioned like AB pipe is there. Suppose this is A here and this is B. So this is the inlet of the pipe, you can say, and this is the outlet of the pipe. And the length of the pipe is L. So how many things are here? And this is the velocity of the fluid flow through this pipe it is flowing. So what are the parameters we are considering here? First one is let it consider L. L is the length of the pipe. Next point is D. D is the diameter of the pipe. And next is V. V is the velocity of the fluid flow which is flowing through the pipe. Next is H. H is the total head which is available at the inlet of the pipe. Now this is the total head. That means from the liquid surface, if you consider two sections in this fluid flow, one section is this one, another section you can consider this one. So if you want to apply the Bernoulli's equation when the fluid is flowing through the pipe, we can apply by considering this is one section, this is another one section. Or else just we consider this is the section of fluid surface level. At the entry of the pipe, at the inlet of the pipe, what is the head is situated. So from the height from the total, top surface to this center line of this fluid, you can say, or the center line of the pipe. So this is the head. Head, the total head at the inlet of the pipe, you can say. So this is total head at the inlet of the pipe. At the inlet of pipe. And this is about length, as I told you. And this is about diameter. And this is about the velocity. So these are the terms are there. Now, when the fluid is flowing through a pipe, we need to consider the losses of fluid flow in the pipe. So what kind of losses need to be considered? So here, though the fluid is flowing through the pipe, we need to consider major loss, that is due to the friction loss. So let's consider the HF. HF is the head loss or loss of head, you can say loss of head due to the friction. So when you're considering this due to the friction, we need to consider also when you're considering the major loss, we need to consider again F. F is the coefficient of friction actually. F is the coefficient of friction, because we are talking about the major loss, and the major loss is basically due to the friction in the pipe and the fluid flow. And so that we need to consider the F also. So what we need to calculate, we need to find out two things. One is weight of the fluid, another one is total head at the end of the pipe. So the head which is available at the end of the pipe is nothing but outlet of the pipe. So now we can write the total head at the end of the pipe. Let's write it again. The total head at the end of pipe, that means at this point what is the head is present, end of pipe, okay, equal to, we can write what is the head at the inlet, total head at inlet minus the head loss due to friction. Head loss due to friction. Head loss due to friction is nothing but HF. And few other losses also there, that is minor loss, like when it is entering to the inlet pipe and when it is exiting from the pipe. So the minor loss can be neglected. So when we are discussing about the total head at the end of the pipe, at this point at the end of the pipe, so here we are considering the total head at the inlet. That means what is the head is present at this inlet position, like when it is entering to this pipe, what was the head present at the inlet condition, and after flowing through the pipe, what is the loss happened during the fluid flow from A point to B point. So that is HF. Okay, in between this fluid flow we have neglected the minor losses. So here we can mention minor loss can be neglected. Minor loss is neglected, that you can mention here, one more bracket. Okay, so here now what we will do, we need to find, this is one point, okay, and we can write what here, we can write as an equation, like what is the equation. Now total head at the inlet is H, and what is the value of HF? HF we know that by Darcy-Weis equation, we know the formula, that is HF equal to 4F LV square, 4F LV square by 2dg. So this one is the major loss. You can give an equation of 1. So this is one thing what we have calculated, total head at the end of the pipe at this point. Now second point, what? Weight of the fluid. Now weight of the fluid W we can write in terms of, as I can say, W equal to weight of the fluid which is flowing per second. W equal to, we can write in terms of mg, you can, if you want to write, we can write it, and this m term, the mass term, we can write in terms of rho and v, because we know that rho equal to mass by volume and m equal to rho into v we can write. So here we can write rho into g into volume of water or volume of fluid flowing per second, so that is v. So this one also again we can write, this is rho g, and the volume part we can write what? Area into this one, we can rho g into AB. AB means the sense the volume of water per second. So the volume of water per second, we can write area into velocity. So again this one we can write rho g. What is the area of this part? Area of the part we can write pi by 4 d square. Though it is a pipe one, we can take this is, and v. Okay. Now this is the weight of the fluid, weight of the water or fluid which is flowing per through the pipe per second. Now what is our ultimate goal? Ultimate goal is you need to find out the power transmission through the pipes. Okay, so power transmission through the pipe is nothing but, we can calculate very simple, P equal to, we can write the power transmission through the pipe P, we can write that is nothing but weight of the water per flowing per second into the head at the outlet, head at outlet condition. If you want to write, I can write like this. As I told you, the power transmission basically depends upon these two things, weight of the fluid and the head at the outlet condition. So this one, these two things we have already got there, like W equal to what? We got this one rho g. Let's write this value rho g. This is pi by 4 d square into v, and multiply, just you multiply this one, H at the outlet. H at the outlet condition is what? This one. This one we can give a equation 2. Previous one equation 1, and this one you can give equation 2. So now what is our ultimate goal? We need to find out the power at the transmitted at the outlet of the pipe. This is W, and H outlet equal to, this one we can write, let's give a bracket, because two terms are there. One is H, the total head at the inlet, and one is head loss. So that is 4F LV square by 2dg. This is bracket close. Okay, now this is the this much watt we can write, or if you want to write in terms of kilowatt, just you can divide into divide here 1000 value on that. So that also you can write here like rho g by 1000, rho g by 1000 into this area value. We can write this is pi by 4 d square and v, and here you multiply of this h minus 4f lv square, 4f lv square by 2 dg. Same formula, just I am writing this much kilowatt. This is our equation 3. This is our equation 3. This is about the power transmitted. Okay, power transmitted at the outlet of the pipe. So this is what we required. Apart from this, also we have some other terms. When you calculating the power, we can calculate the efficiency part. So efficiency also directly we can relate to the power term, efficiency of the power transmission. So that we can write, we know that efficiency equal to, we can write power available at the outlet condition and what is the power available at the inlet condition. So by using that formula, we can find out the efficiency. Okay, so let me go to the next one. So here I can write efficiency of power transmission. That what is the power transmitted here? What is the efficiency of power transmission? We can write. So we can write power available at the outlet. Power available at the outlet of the pipe divided by what is the power supplied at the inlet of the pipe. So here we can write power supplied at inlet. Okay, and here what is the power available? This one is power available at the outlet condition. So what we can write at the available outlet condition means, that means we can write weight of the water supply or weight of the water at the outlet condition into the head at the outlet condition, that means W into H. And what is the power supplied at the inlet condition? That means we can write weight of the water at the inlet condition and head of the inlet, that means W again H. Here this H is inlet, head at the inlet condition, and this in the denominator, in the numerator, the H at the outlet condition. So here we can write H minus HF, because the same thing we have written here. If you see H minus HF, this one. Okay, so here also the same H minus HF we can write. Now if you write this one, we can cancel this WW and we can get it what? Now, H minus HF by head at the inlet condition. This cancel this one and we can write this. This one you can give equation 4. Previously up to equation 3 we have given. Now we can give equation 4. So this is for the efficiency of the power transmission. Now another point what we can write, what is the condition for the maximum power transmission? What is the condition? What is the condition for maximum power transmission? Maximum power transmission. This is one, conditions we can say, or we can say like how much power we got and where at what optimum condition we can get the maximum power transmission. So for this we need to consider the previous equation what we got here, equation 3, and we need to just we can find out the maximum by derivating the power equation. So what we need to do, we just need to derive derivative of the power equation with respect to V. That should be equal to 0. So what we can write now, derivative of power. So power equation what we got there, just to give we can mark it in terms of square bracket here, rho g by 1000, there what the area, pi by 4 d square into pi by 4 d square into V into H. Yeah, V again. Here we can give HV. Okay, already we have given here V, or we can give HV here and just we can strike it off, minus the loss 4FLV square by 2DG bracket close square bracket close equal to 0. Now we just need to derive this power term with respect to delta V dV. Now if you derive this one, what will you can see rho g by 1000, this constant term, let's take it outside. So rho g by 1000, and this one pi by 4 d square also can be taken out. There is no relation of this, all are constant only. And derivative of HB, so here dV by dB, so H will be come out, so we can write this is H minus derivative of only HB I did, so this is V, and here 4F LV square by 2DG. So all this term constant term we can take out, and this is dV square by dV. So this is actually okay. No, 1 minute. Here actually this V term is there. You can see this V term is there. What we have done. Now this V term we have multiplied in the HB and here LV square. So here we can write this is LVQ. Remaining terms are like all are constant term. Let's take it out. And V term which was there here, that I have taken inside HB, and minus 4F LV square initially there. Now V was multiplied here, so LVQ. So now we need to just derive this 4F LV L by 2DG. Let take it out, and derivative of VQ. So this one we can write 4 LF, and this is 3V square by 2DG equal to 0. Now what I'll do, this constant term what is there outside of the bracket, let's take it to this side and make it 0 here, and remaining terms what will be there, I can write H minus this 3 again 3, let's take it out, and this is remaining terms what I can write like 4 LF V square by 2DG equal to 0. Now if you see this part is nothing but the head loss part, 4F LV square by 2DG, the head loss due to the friction. So what we can put here H minus 3 HF, H minus 3 HF equal to 0, or we can write HF equal to 3 HF. So here the head loss due to the friction, HF equal to, I can write H by 3. H by 3. This is our final conclusion when we can consider the maximum power transmission. So this equation states that maximum transmission can be observed when the flow through the pipe, when the loss of head due to friction is 1/3 of the total head of the inlet current, because H is what? H is, I already told you here, H is the nothing but the total head at the inlet of the pipe. Okay, so when we can get the maximum power transmission, when the loss of head will be equal to the total head, 1/3 of the total head of the inlet condition. So this is the condition for this. One more term we can discuss, that is maximum power. That is maximum power efficiency, or maximum efficiency of the transmitted power. We can write maximum efficiency of power transmitted or transmitted power. Okay, so these things also we can write here, like previously what we got here, efficiency, a maximum, this is only efficiency, correct? What we derived here, this is only efficiency. Now maximum efficiency of power, transmitted power, how to identify? From the same equation we need to consider. This one we can give equation 5, and here we can write, now previously we have seen that efficiency equal to H minus HF by H. So to find out the maximum efficiency of the transmitted power, we need to just put the value of HF equal to H by 3 here. So put the value of HF equal to H by 3, that is nothing by H by 3 divided by H. So what we will get here, h by h. Let me write in this way, h by h minus h by 3h. Now h cancel here. So efficiency, what we can write, 1 minus 1 by 3. So 1 minus 1 by 3 nothing but we can get 2 by 3. So 2 by 3 is nothing but what we can write. This is 66.7%. Yeah, 66.7%. 66.7. If I divide this one, what I'll get here? Now 0.667, like that. Unlimited will get like this. So if we can write in percentage, means that is 66.7%. So this is the maximum efficiency of transmission of power. This one, 66.7%. And when the maximum power can be transmitted, when the loss of head will be equal to the 1/3 of the head at the inlet condition. And this is the efficiency of the power transmitted. And this is the power transmitted. Power transmission through the pipes. So these are the terms which is related to this power transmission through the pipe. I hope you understand this concept. If you are having any doubts and query regarding this, you can give a comment on the comment box. Thank you all.